In this video, I'm going to demonstrate how to use SPSS to conduct the Friedman test, which is the non-parametric equivalent of the one-way analysis of variance with repeated measures. So here we see our fictional study where we have 10 research participants, which are 10 randomly chosen students who observed 3 different instructors, and the participants were asked to provide a rating between 1 and 3 assigned to each of the instructors, where the value of 1 indicated the lowest rating for that particular across the 3 instructors, and the students perceived a rating of 3 as the highest quality instructor. So for example, participant 1 viewed instructor 1 as the lowest, instructor 2 as the middle, and instructor 3 as the highest quality, with a wide range of responses. Now before we move through to conducting the Friedman non-parametric statistical test, under variable view, when we set up these variables for the ratings of instructors 1, 2, and 3, make sure that the measure is in ordinal for each of those 3 measures. And that's going to be a necessary requirement when conducting the analysis. So in conducting the Friedman analysis, I'm going to go to Analyze, Non-Parametric Tests, and then Legacy Dialogues, and now I have K-related samples. And so I'm just going to highlight all 3 and bring those over to test variables. Under statistics, I can click descriptives or quartiles. So if we want to include those data in our interpretation and presentation, we can do that as well, and that'll allow that calculation. We see a couple of other approaches here, but I'm just going to zero in on the Friedman approach here. So I'm going to hit OK. And what we see here is we have our descriptive statistics with the quartiles of 25, 50th, and 75th percentiles. We have the mean, the average rating for each of the 3 instructors. And so just by looking at this, we can see that instructor 1 on average had the lowest ratings. Instructor 2 was somewhere in the middle. Actually, not quite in the middle, but closer to instructor 3, and that's summarized on the second table as well. But what we're looking for in terms of statistical significance is the test statistic in this third table. So we have our Friedman chi-square value, our chi-square obtained of 9.8. Since we had 3 instructors, the degrees of freedom are 3 minus 1, so it's 2, and the p-value of 0.007 indicates that this is statistically significant, indicating that there is a statistically significant difference between these 3 different instructors. However, that's going to necessitate conducting a pairwise statistical approach next. Now to do that, we have to use the Wilcoxon approach to that. So I'm going to go back up to Analyze. I'm going to go to Non-Parametric Tests, Legacy Dialogues, and now I want 2 related samples. So I know I have 3 here, but to do the post hoc testing, and we do the post hoc testing because of the result of the Friedman chi-square test being less than 0.05. So I'm going to click 2 related samples, and what I need to do now is set up my pairs that I wish to examine. So I'm just going to take instructor 1, I'm going to pull that over here. Now variable 2 is highlighted, so I'm just going to click instructor 2 and pull that over. Now for the next pair, I'm going to click instructor 1. For the second variable, I'm going to click instructor 3, and I'm going to pull that over. Now we have one more pair to put in here, and that's a comparison between instructor 2 and instructor 3. So I'm going to click 2, then I'm going to click 3, and that 4th row we can just ignore. Under options, we can put in our descriptives and quartiles. as well for our paired comparison. So I'm just going to leave those here to illustrate how those are calculated, and I hit continue. And we have a number of different approaches here. I'm going to ignore these lower three since I want to focus on zero in on the Wilcoxon uh, uh, test for paired samples. And I hit OK, and you'll notice how when we have our output window open and we carry out the analysis, the new analysis will be appended to the previous one. So I'm just going to scroll down here, and once again you see I've generated descriptive statistics again as we did in the first step, so I'm just going to skip that. Here we see a summary of the ranks of the pairwise comparisons, but what I want to zero in here are the test statistics for statistical significance. And so what we see here summarized in the first heading is instructor 1 and instructor 2, and this uses a z-statistic, and it calculates a p-value of 0.024. For instructor 1 and 3, we see a much lower p-value of 0.004, and instructor 2 and 3, the p-value of 0.589 is quite large, quite a bit larger than 0.05, which is our typical standard, and so this one we would determine not to be statistically different from each other. Now, an important point to make here, and that's not, there does not seem to be an option in SPSS to do that. These p-values have to be interpreted with respect to the Bonferroni correction factor. And what that correction factor is it takes our overall type 1 error rate of 0.05, and we have to divide that by 3. And when we divide it by 3, we end up with a value of 0.017. And so the 0.017 is now the corrected type 1 error rate for the pairwise comparison. So when we conduct pairwise comparisons in a repeated manner this way, that will naturally tend to increase the risk of committing a type 1 error. And to counterbalance that, we have to divide our p-value. So we actually set a new threshold of 0.017. And in that sense, the difference between instructor 1 and instructor 2, although it's less than 0.05, it's larger than 0.017. So we would conclude that following the Bonferroni adjustment, the difference in the ranks between instructors 1 and 2 are not statistically different. Instructor 2 and 3 hasn't changed, but since 0.004 is smaller than 0.017, we would conclude that the only statistically significant difference exists between instructor 1 and instructor 3 on a statistical level. So this ends this video on conducting the Friedman test of K-related samples using SPSS.